Welcome back. In this module, we will provide an overview of logistic regression. One simple objective. So, in previous lectures, we looked at how we could derive a confidence value from a classification algorithm and then use that confidence value as a way to kind of trade off in your results between things like precision and recall. Now, when you think about it, if instead of defining a hard class label, you're defining a numeric value, this may have led some of you to wonder, well, can we use a regression approach for a classification task? And the answer simply is yes, you can. So one very popular approach to using regression-based model for classification is what's called logistic regression. And it uses a logistic function, which is shown here. It can be, there's kind of two common ways that it can be written out, but they're both equivalent. I've also included the derivative because, as you may have guessed, that this, the approach to solving this function will probably involve gradient descent, just like we saw with linear regression. Additionally, for those of you who might be familiar with neural networks or deep learning, logistic regression can be thought of as a very simple neural model that consists of just one neuron. So here is how it looks written out. We have our logistic function, sigma. I subscripted it with W, which are the weights. And whereas before, what we had with linear regression, we just had f of x equals W transpose multiplied by your x vector. Here, that is just an exponent in the base of the natural logarithm in the denominator here. But just like with everything else that we've talked about in the class that's feature-based, we're having m number of features. However, there are m plus 1 components in w and x. We will treat x0 as being a 1 because w0, that's our bias. That's what's kind of positioning the function on the graph. And just like with linear regression, the whole idea is we just want to find a w such that this loss function is minimized. And this is the same loss function that we've been using all along. It's just a sum of the error squared. And the only difference is, now we have this logistic function here. So since that logistic function is obviously not linear, this is going to be a little bit more involved to find the derivative. Now, not, burdensomely so, because as I showed you in the previous slide, we know how to find the derivative for a logistic function. So here we're going to use a bit of calculus, and we're going to use it, twice. Once to derive or to find the derivative of the logistic function, and then again, since the logistic function is embedded inside the loss function, you need to use something called the chain rule that allows us to find derivative of composed functions. Now, we will go over this in much more detail in a calculus review later on. The point of this lecture is just to give you a bit of the intuition. So we have our logistic function. We look at it as two different functions, 1 over x and 1 plus e to the negative x, and these are composed together, where you can think of this as being f of g to the f of g of x. And you find the derivative for both, and by the chain rule they get combined, and it ends up looking like this. And then we can do a little bit of algebra, and it comes out that the derivative of the logistic function is simply the logistic function multiplied by 1 minus the logistic function, which is a handy thing to have. Using the chain rule again, we can now solve for the whole derivative of the loss function, and then we end up with this. Now this is what we're going to use throughout gradient descent to update the gradient as we do each iteration, just like what we had with linear regression. So why use logistic regression? Well, it provides a number that can be viewed as a probability of class membership, which a lot of people are more comfortable using what could be treated as something coming out of an actual probability distribution as opposed to a confidence provided just from a non-probabilistic machine learning algorithm. This provides a very simple regression function that you can actually go look at and actually see the function that gets learned. Unlike something like a deep neural network where you're going to have a whole lot of layers, this is only one single function, looks just like what we showed in the slide, except that exponent of the base of the natural logarithm, you're going to have a whole bunch of weights for each of the features that you use. But you can actually look at those and see what they are and which ones have a higher weight and so on. And of course, this is very simple to implement. Not so much an issue nowadays. We have a lot of mature machine learning packages, but if you're really in a pinch and you want to write something from scratch, this one's an easy thing to do. And it actually also gets decent results oftentimes, and it's a nice, simple thing, doesn't have a lot of hyperparameters, to just throw at a problem and see what it can do. Decision tree is kind of the same in that regard. Very simple things to throw at a problem, just get an initial feeling of what can happen before we get into something more complicated like a deep neural net or XGBoost, where there's a lot of hyperparameters to think about. These things are kind of nice out of the box. So that's it for this quick lecture on logistic regression. Thank you very much.